Today I'm going to present a video on working stress method. So please kindly subscribe to Civil eLearn for more videos. The working stress method is based on the elastic theory, which is also known as working stress in the concrete. The working stress in the concrete is equal to the ultimate compressive strength of the concrete by factor of safety. In this case, the factor of safety is taken as 3 to 4. And the permissible stresses in the steel is obtained by dividing the yield stress of the steel by a suitable factor of safety. In this case, the factor of safety for steel is taken as 1.8 to 2. The design load is also known as the critical load, which the structure may be subjected in its lifetime. The load is also known as working load or service load. The basic assumptions made in the working stress method. These are all the assumptions made in the working stress method for designing the structure. At any cross section, the plane section remains plane before and after bending. Let us take a rectangular cross section. After bending, also the particular section remains plane, and the tensile stresses in the concrete are taken as 0 if they take stresses also, but the tensile stresses are taken up only by the steel reinforcement and none by the concrete, except as otherwise specified. The stress-strain relationship of steel and concrete under working loads is a straight line. The modular ratio is taken as 280 by 3 sigma CBC. This is the modular ratio equation. How to calculate the modular ratio? So actually the concrete section is the RCC section is a composite section in which the steel is there and concrete is there. If we apply the load on that particular cross section, the steel will act differently and the concrete will act differently. So in this case, for a length of L, the steel bar and concrete bar placed and given supports at the ends, and a load of P is acting on both sides. Composite section consists of two bars, one concrete and other steel, bonded together with ended plugs and subjected to a compressive load of P. In this case, we are considering these are the constants, that is E suffix S is equal to modulus of elasticity of steel, EC is equal to modulus of elasticity of concrete, A is the area of each bar, PS is equal to load carried by the steel, and PC is equal to load carried by the concrete. In this case, total load P is equal to PS plus PC. Delta, that means deflection. Delta is equal to PL by AE, as you already studied in the strength of materials, that is deflection is equal to PL by AE. The same formula we are using here, that is delta is equal to PS into L divided by AES. That means the deflection in the steel is equal to the deflection in the concrete. As the end plugs are there, the deflections will be equal. So by using this equation, PS by PC is equal to ES by EC. Here L is the same one, so PS by PC is equal to ES by EC. Then M is equal to ES by EC. This is the stress block. This is the singly reinforced rectangular cross section, which is having a width of B and effective depth of D, and the total depth means that is from top of the beam to the bottom of the beam, and these are the tension reinforcement, which is known as area of steel in tension zone. So for this particular section, if we draw the stress and strain curves, here we will get the strain of epsilon sy, and in the top it is epsilon cu, because here there is no steel section, that's why we will get epsilon cu, and this is the 0.2%, that is proof stress. And the stress diagram Here we will get FCK. In this case, the tension reinforcement is there in the tension zone. That's why we will get a tension of capital T. The difference between, the distance between the compression zone to tension zone is known as Z. That is known as lever arm. Position of neutral axis of a singly reinforced concrete beam section. As we already uh, seen in the previous slide, that is, small d is the effective depth, capital D is the total depth, and B is the width of the beam, and this is the area of steel reinforcement in the tension zone. So in this case, epsilon s is equal to sigma st by Es. Es means modulus of elasticity of the steel section. Epsilon c means the strain in the concrete. In this case, the sigma cbc, that is the stresses, and sigma st by m, where k is equal to m sigma cbc by m sigma cbc plus sigma st. K is a constant, and n is equal to k into d, that is the neutral axis, critical neutral axis. Nc is equal to k into d. Actual neutral axis. How to find out the actual neutral axis? This is the formula for calculating the actual neutral axis for a singly reinforced beam. That is, B Na square by 2 is equal to m into ast into d minus Na. That is, m is the modular ratio, and ast is the area of steel in the tension zone, and d is the effective depth, Na is the actual neutral axis, and B is the width of the beam. In this case, Nc is equal to, that means critical neutral axis is equal to k into d. Here k is the neutral axis constant and d is the effective depth of the section. By using this equation, we can find out the Na value, and by using a Nc formula, we calculate the Nc value. If Na is less than Nc, the section is under reinforced, and Na is equal to Nc, the balanced section. If Na is greater than Nc, the section is over reinforced. Generally, the over reinforced sections are not preferred for design, and balanced section is also not possible, so it's better to design the section for under reinforced sections. Under reinforced section, a section in which the area of the steel reinforcement provided is less than that is required for a balanced section, which is also known as a under reinforced section. In this section, actually the steel will fail fast and further the concrete will fail, so the failure is not sudden. In the over reinforced section, a section in which area of steel reinforcement provided is more than that is required for a balanced section, which is also known as a under reinforced section. Over reinforced section. In this section, the stress in the concrete reaches its maximum allowable value. The steel in the steel is lesser than its allowable value. In this case, the concrete will fail and the steel will not fail. So, the concrete failure is a sudden failure because concrete is a brittle material, so the failure will be sudden. So, reinforced sections are not preferred for construction purpose. In actual engineering applications, it is desirable to obtain an under-reinforced section because the steel will yield first and after the concrete starts yielding, which will give sufficient warning before failure. Whereas in the over-reinforced section, the concrete attains its maximum stress fast and the failure will be sudden. The moment of resistance. Moment of resistance means this is the resisting moment offered by a beam section to resist the bending moment at the section. So the resistance moment is equal to total compression or total tension into lever arm. Lever arm, as we already studied in the previous case, that is, lever arm means the distance between the total compression to the total tension. The distance between the point of application of compressive force and the point of application of tensile force is called lever arm. The centroid of the compressive force is at a distance of n by 3 from the top of the centroid of tensile forces is at the center of the tensile steel reinforcement. So the lever arm is d minus n by 3 and the factor for lever arm is 1 minus k by 3. Moment of resistance for balanced section M is equal to QBT square. Q is the factor of bending moment, that is half into sigma CBC into K into J. In this case, K is the neutral axis factor. Sigma CBC is allowable bending stresses in the concrete. Sigma ST is the allowable stresses in the steel. For mild steel, the sigma ST value is 140 Newton per mm square, and for HYST it is 230 Newton per mm square, and J is equal to 1 minus K by 3. K is equal to M sigma CBC by M sigma CBC plus sigma ST. In this case, K is the neutral axis factor. So, in ISO 56-2000, Table 21, the permissible stresses in concrete are given for different grades of concretes. For M10 it is sigma. For M10 bending in permissible stresses in compression bending it is 3, and direct it is 2.5. Permissible stresses in bonding it is 0. So based on these values we can take the values of sigma CBC values from this table. These are the types of problems. For designing a beam section, the bending moment and permissible stresses, the area of steel in the tension zone is calculated by using this formula, that is M by sigma ST into JD. And for determining the moment of resistance, first of all we have to calculate the actual neutral axis, that is B NA square by 2 is equal to M into AST into D minus NA. In this case, B is the width of the beam, NA is the actual neutral axis, M is the modular ratio, that is 280 by 3 sigma CBC, and AST is the area of steel in the tension zone, and D is the effective depth. And after calculating this equation, we will get the actual neutral axis value. Then calculate the critical neutral axis, that is NC is equal to KD. If NA is less than NC, that particular section is known as under reinforced section. And for that under reinforced section, the moment of resistance formula is sigma ST into AST into D minus NA by 3. If NA is greater than NC, that particular section is known as over reinforced section. The moment of resistance for over reinforced section is PNA into sigma CBC by 2 into D minus NA by 3. In this case, you have to notice one thing. If the section is under reinforced, the failure will be in the steel portion. That's why the moment of resistance equation is mainly regarding the sigma ST into AST. That means regarding the steel only. In the over reinforced section, the failure will be sudden, so the concrete will fail fast. That's why the moment of resistance is based on the concrete, that is PNA into sigma CBC by 2.